Imagine a string is fixed between two supports. A string of length L fixed between two supports. Okay. Now, pull down, deform it, and leave it. Then the string executes simple harmonic motion. Okay. It appears this system like a wave traveling forward and wave reflected from this boundary and coming backward direction. Okay. So, in this medium like two waves are traveling forward and backward. Okay. So, in the same medium two waves are traveling forward and backward. How to calculate the wave equation? Let us discuss now. Okay. That type of wave is called a stationary wave. Okay. Let me look at the superposition of waves. Okay. Superposition of waves, because we need this concept here to calculate the wavelength and all. Superposition of waves. Okay. Let me discuss about the superposition of waves with reference to sound waves also, which are longitudinal. Of course, sound waves are longitudinal waves. Okay, fine. Imagine there is a reflector here. Okay. So, S is the source. Of sound. Okay. Afterwards, I am going to apply the same concept to the transverse wave, and there is a medium particles. Okay. The medium particles. When a wave is propagating towards positive x-axis, it is reflected by a wall. The wave will reflected back. Okay. Now, I want to write the equation for a particle which is a distance x from the origin. Okay. If the reflector is not there, let us write this as a reflector. Okay. If reflector is not there, the wave travels only in one direction, that is called progressive wave. When reflector is there, it reflects. And one more thing you have to remember here is, whenever a wave is reflected by a denser medium or a rigid support, phase change is 180 degrees or pi radians. Whenever wave is reflected by a rarer medium or a free end, there is no change in phase. Once again, I repeat, this is a very important factor. When any wave reflected by a denser medium or rigid support, phase changes pi radians or 180 degrees. Okay. It reverses like this. Okay. If the wave is reflected by a rarer medium, there is no change in phase. Okay. Depends on the condition, this one. Okay. Now, in the forward direction, the wave is y1, in the reflect direction, the wave is y2. Okay. In forward direction, the wave is y1, in the reflected direction, due to reflection, the wave is y2. Okay. Now, the particles of the medium is subjected to two disturbances simultaneously. The particles of the medium is subjected to two disturbance. When reflector is not there, the particle is subjected to only one disturbance, but now there are two disturbances. So, the superposition of these two disturbances will decide the displacement of the particle. Okay. This phenomena usually we call it as superposition of waves. Now, I am applying for longitudinal waves, afterwards you can apply even for transverse waves also. Now, the resultant displacement y, the resultant displacement of the particle y is sum of these two, sum of these two. Okay. This equation is called superposition principle. This is a very, very important principle in physics. Superposition principle. Superposition principle. Okay. The resultant displacement is sum of the displacement due to two waves, y1 plus y2. Now, I am going to calculate this expression. I know that y1 is a sin omega t minus kx. The displacement due to forward wave is y1 is a sin omega t minus kx, plus in the reflected wave y is equal to a sin omega t plus kx. Of course, if there is a phase change, I have to add here pi. Phase change I have to add. Okay. So, depending on the phase change, I should add either 0 or pi. Let us say there is no phase change. This represents a wave travelling towards positive direction. This represents a wave travelling towards negative x direction. Sum of these two, by using little bit trigonometry, I can find the resultant wave y is equal to 2a cos kx sin omega t, or okay, depending on the phase you may get y is equal to 2a sin kx cos omega t. You may get any of this equation. Of course, depending on individual waves and phase change, you may get cos and sin can be interchanged. This equation is called stationary wave equation. This equation is called stationary wave equation. Okay. So, when the stationary wave is formed, when two progressive waves travelling in opposite direction, a stationary wave is formed. Okay. So, whatever you are sending energy this side, the same energy is coming back, the rate of transfer of energy is 0. Okay. Whereas, if reflector is not there, the energy is continuous flowing one direction. So, rate of transfer of energy is there, that is called progressive waves. Whenever you keep a reflector, the same energy comes back. So, here I am, of course, I am assuming that reflector does not absorb any energy, that is why I am writing the same A in the reflected wave also. Okay. So, let us discuss this stationary wave. The physics behind this mathematical equation, stationary wave. Y is equal to 2a cos kx sin omega t. This represents stationary wave. Stationary wave. Of course, 2a cos sin kx cos omega t. Sin and cos can be interchanged. cos, sin, cos, anything is possible depending on the phase change and individual waves. Now, y is equal to a sin omega t minus kx. This represents progressive wave. This represents stationary wave. In progressive wave, when a progressive wave is traveling through the medium, every particle of the medium vibrates same amplitude. Everywhere the amplitude of the particle is same. Whereas in stationary wave, the amplitude which is 2a cos kx, or it can be 2a sin kx also possible. Okay. 2a cos kx, that means amplitude depends on position x. Okay. We know that y depends on both x and t. X is the position, t is the time. Okay. So, the amplitude depends on position x. That means all the particles, even though vibrating the same frequency, but not with same amplitude. Amplitude varies from position to position. So, if I plot a graph, even if I write a graph for this, y is equal to 2a sin kx cos omega t, x is equal to 0, the amplitude is 0, sin 0 is 0. Of course, here when x is equal to 0, the amplitude is maximum. So, if I write a stationary wave, simplest case, okay. Let us say x is equal to 0 to x is equal to L, where L is the length of string. At this place amplitude is 0. At this place amplitude is maximum, again amplitude is 0, again amplitude is maximum, like this. Okay. Let us say when x is equal to 0, the amplitude of stationary wave AS is 0. Okay. Let us x is equal to lambda by 4. Okay. Let us say where lambda is the wavelength, the amplitude of stationary wave is 2a. Okay. Similarly, x is equal to lambda by 2, again AS is equal to 0, like this. At different places the amplitudes are varying. Okay. At some places amplitude is 0, at some places amplitude is maximum. So, the amplitude maximum points are called antinodes. These are called antinodes, these are called nodes. Okay. So, at antinode, A represents antinode, the displacement is 2a. Of course, this is antinode anyhow. So, when two waves are propagating to the medium, at some places the particles are not at all vibrating, the amplitude is 0, those are called nodes, these are called nodes. At some places the amplitude is maximum, they are called antinodes. Okay. Nodes and antinodes are formed in medium. The distance between node, successive node and antinode is lambda by 4. The distance between node and antinode, successive node and antinode is lambda by 4. The distance between two successive nodes is lambda by 2. Sometimes this lambda by 2 is called loop length. So, the same type of wave we can observe when you vibrate a stretched string. When you vibrate a stretched string, the same type of stationary waves we can observe in the string. Suppose if you touch at midpoint or somewhere here, then the mode of vibration may change. The mode of vibration may change like this. It can. So, like this, by touching at different points, we can change the mode of vibrations, like fundamental mode, first overtone, like this one. So, this all about the types of waves formed in the different cases. So, now, finally, what we discussed today is there are two types of waves. One is longitudinal wave, the other one is transverse wave. Okay. So, depending on the propagation of the medium particles, we are divided into two parts, longitudinal and transverse. Again, in longitudinal or in transverse, okay, there are two types again. One is progressive wave, where there is no reflection of sound energy, that is called progressive wave. If you put a reflector there, the same wave turns back, then superposition of two waves takes place. That superposition of two waves will form a stationary wave. Okay. So, a stationary wave can be transverse as well as longitudinal. Okay. So, in the next class, we are going to discuss the how to calculate the frequency of this vibrating string and how to excite different modes and the loss of vibrating string and how to verify it by using sonometer.